welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Good afternoon and welcome all to the Agilent Technologies webcast titled HSPA Plus and LTE Test Challenges for Multi-Format UE Developers. My name is Marcellus Bronner and I will be your moderator for this session. Our presenter today is Jody Selmer. Jody is a product planner at Agilent Technologies specializing in HSPA Plus HSPA technologies. She is based in Agilent in the United States and has worked at Agilent and HP for more than 25 years. Jody graduated from the University of Wisconsin in Madison with a BS degree in electrical and computer engineering. Later, she received a master in electrical engineering from the University of Massachusetts in Amherst. Even in college, Jody was most interested in communications and wireless technologies. Jody is married and has a daughter also considering a career in engineering. She enjoys walking, reading, singing, and cross-country skiing. So, we will begin our webcast in a moment. First of all, I want to make you a little bit familiar with the system. So for everyone's comfort, this is a lecture-style meeting. However, you can send questions to Jody in writing at any time during the session using the question and answer window of the WebEx meeting messenger. This is on the lower right side of your screen. Jody will answer your questions at the end of the session. In the Q&A window, be sure to select all panelists before sending the questions so that we can see your messages. However, even if your question will be published to all, we will keep your identity private. Please be reminded that this is a webcast which will be recorded so that you can review afterwards and share with your colleagues at any time. Right after this web seminar, you will also get an email with additional information how to access this recording. And so now I'm passing over to Jody. Welcome, Jody.
Thanks, Marcellus. I'm happy to be here today to talk to you about HSPA Plus and LTE test challenges for multi-format user equipment developers. So here is our agenda for today. After a brief introduction, I will talk about the evolution of the technologies that are going on today with a focus on the frequency division duplex technologies. Then we'll talk about the technologies in a bit more detail next. We'll go into a market overview where I give a bit more information about the industry drivers that are causing these technologies to enhance. We'll spend most of our time here talking about the future for multi-format developers and what all of this means. Okay, so let's start with an introduction considering today's environment for UE development and where it might change in the future. So today we know that LTE, which stands for long-term evolution, is hot in the market. But so is 2G and 3G and 3.5G technologies, which are led by HSPA Plus, or high-speed packet access. So both of these technologies are around today and are being enhanced as higher data throughput demands and more applications are being developed as well. So the demands on device developers with these multiple technologies continue to increase. And as we move into 4G with Lte-Advanced, even more demands will make the job more complex and challenging. So today we'll talk a bit about the trends and opportunities with HSPA Plus and the challenges that are faced by handset developers in delivering reliable performance with these higher data rates and the multitude of applications on devices today. We'll talk about the test needs as well with these different technologies, and we'll briefly touch on some solutions from Agilent. So now let's look at the evolution of 3GPP, the standards body for these different technologies. And in particular, we'll talk about the frequency division duplex technologies. So the 3GPP standards continue to evolve. We started with GSM many years ago, and then moved into WCDMA with enhancements then to HSDPA and HSUPA, and further enhancements to HSPA Plus and MIMO, or multiple input, multiple output technologies. Today we are here in Release 8 and working on implementing dual carrier HSDPA as well as LTE with 2x2 MIMO. So you can see that today we're at data rates here of about 42 megabits per second with 11 megabits on the uplink for the HSPA technologies. For the LTE technologies today, we're at a maximum rate of about 150 megabits per second in the downlink and 51 in the uplink. As we move forward, people are starting to look at releases 9, 10, and 11. These are the next releases that the 3GPP standards are defining. And you can see the data rates continue to increase, almost an order of magnitude by the time we get to release 11. You can also see that the data rates for HSPA are keeping up with those for LTE. In fact, even here in release 11, you can see that the HSPA data rates are comparable with those achieved by LTE or soon to be achieved by LTE with release 9. It's important to remember that the frequency division duplex, or the FDD part of the standards, is just one piece. There are also TDD evolution paths, time division duplex, with technologies like TD-SCDMA and TD-LTE. Those technologies are also important, but today we're going to focus on the FDD side. All right, so let's look at these technologies in a bit more detail and see what they can do for us. So WCDMA is where we started with 3G, and that was a part of Release 99. It was then enhanced to move towards HSPA, or high-speed packet access. And the first improvements that occurred to make this happen, and you'll notice these same types of improvements as I go through the technologies. Two main things are done to improve data rates and increase channel efficiency. The first is to reduce transmission times. So this is the time it takes data to be sent either from the network to the phone or from the phone back to the network. For the change from WCDMA to HSPA, those transmission times were improved by 5. So we went from a 10 millisecond time to 2 milliseconds. The second most common way to increase data rates is to improve modulation, to make it more complex so that more data can be sent in the same bandwidth. And in this case, for HSPA, there was a new downlink modulation type which was introduced to do just that. The third major improvement for HSPA was the ability to allow the phone to send information back to the network about its reception of the data as well as the channel quality. So CQI is channel quality information. So in HSPA, the phone can now report to the network information about the quality of the channel and the data it's receiving, which then allows the network to make changes to improve that channel if required. After HSPA, we moved to HSPA Plus, or Enhanced HSPA. This is part of Release 7 in the standards. Once again, you can see here 2 new modulation types were added to improve throughput. And we are now with HSPA Plus at a maximum 21 megabits per second in the downlink and 11 in the uplink. Okay, what comes next? Well, as we move into Release 8, 9, and 10, there are some additional things that are being done with HSPA+. Another most common way to improve data throughput is to add carriers. So what this means is there are now 2 RF carriers, or up to 4 potentially, with releases 10 and 9 and 10, that allow multiple channels to be transmitted at the same time. So multiple 5 megahertz channels in this case for WCDMA. These channels can be applied in the downlink and the uplink, and multiple antennas are not required for these multiple carriers. However, with MIMO, which is another improvement, multiple input, multiple output, 2 data streams are created and 2 antennas are required at both the network side and the phone side. MIMO is done with different coding on data streams that is then transmitted for diversity reasons, and only requires 1 5 megahertz channel. So through release 10, there are no combinations of multiple carriers and MIMO. As we get beyond release 10, you can see the trend continue. 5 to 8 carriers are now possible, which gives us up to a 40 megahertz aggregate bandwidth with HSPA plus Advanced. This is done in the downlink only and can be combined with MIMO for further improvements in data rate. And another improvement that's being considered is multi-point transmission. So in this case, data is sent from multiple cells, and this does require multiple carriers be used, as well as ARC diversity support in the phone. And once again, this can be combined with MIMO to further improve data rates. So here on the right, you can see a table which summarizes the different data rate improvements that can be achieved with these different technologies. And you can look at that later. Okay, so that's HSPA and how it is planning to advance over time. Now let's look at LTE, or long-term evolution, and what its characteristics are like. So I talked about the transmission times. You can see here that once again we have decreased our transmission times by a factor of 4. For HSPA, we were at 2 milliseconds. Here for LTE, we're now down to 0.5 milliseconds. LTE also uses different modulation types to improve efficiency and allow more data to be transmitted in the same bandwidth. So in the downlink, OFDMA, or orthogonal frequency division multiple access, is used. On the uplink side, single carrier frequency division multiple access is used. A big difference between LTE and HSPA is the use of subcarriers with LTE, and these are orthogonal channels which are transmitted together and very close together and carry data just as regular channels do. And when many subcarriers are combined, it basically allows you to transmit the same amount of data as you could with a standard carrier. So those are used with LTE. MIMO is also used with LTE, very common to use 2x2 MIMO, and as the chart showed earlier, we'll be moving into 4x4 in the future. The other big difference with LTE that you'll hear about a lot is that LTE is an all-IP network. All data is transmitted over Internet Protocol, and circuit switch data, as traditional voice used to be, is not used. And to do that, an evolved packet core is developed, which is a new network element to allow the all-IP data to flow freely. So with LTE and releases 8 and 9, we can now achieve a downlink, maximum downlink data rate of about 300 megabits per second, and a maximum uplink data rate of about 85 megabits per second. But LTE is also going to advance, so let's take a look at what happens as we get to what they're calling Lte-Advanced. Lte-Advanced has been identified as a true 4G technology, and that is done according to the group Lte-Advanced. This group has defined a set of conditions that must be met for a technology to be called 4G, and Lte-Advanced is the first technology to be attributed as a 4G technology. So what changes as we move towards Lte-Advanced? Well, surprise, it looks just like HSPA. We are doing carrier aggregation, so multiple carriers are being used, just as we did with HSPA. These carriers can be used on both the downlink and the uplink, and can be combined with MIMO. In addition, MIMO is being enhanced, potentially up to 8x8 in the downlink, and 4x4 in the uplink, and also multi-user MIMO is being discussed for Lte-Advanced. Once again, you can see over here a table that summarizes the different data rates for the different advances in technology. Okay, that's a summary of the technologies and how they're changing over time. Now let's take a look at the market and the industry drivers pushing these technologies to change. So there is strong industry support for both HSPA and LTE. You can see there's a large installed base of HSPA operators. According to this, 100% of the WCDMA operators have launched HSPA networks. Over here you can see that HSPA and HSPA Plus are mainstream today. There are 211 network commitments and 152 networks launched today. In addition, there are 49 on this slide commercial DC HSDPA networks. That stands for dual carrier HSDPA. And actually that number has climbed to 62 since this slide was made. On the LTE side, there are 49 commercial networks launched now, and they predict that 119 networks will be launched by the end of this year. On the device side, there's 197 LTE user devices. I'm sure that's larger now. This slide was made in January. For HSPA, there are over 3,000 devices out there, with 182 of them being HSPA Plus. So there's a lot of statistics here, but all of that means there's a big investment going on in the industry with all of these technologies, and it's likely that HSPA and LTE will continue to grow together. Well, the slide says it's all about data rates, but we all know that really isn't true. However, if you look at data rates between HSPA Plus and LTE, and you compare them with similar bandwidths, you can see that the data rates are actually quite comparable. So using a 5 megahertz bandwidth, you can see that HSPA Plus achieves a maximum rate of 42 megabits per second and LTE 37. If you move to a 10 megahertz bandwidth, the maximum rate that HSPA Plus can achieve climbs to 84 megabits per second and LTE to 73. If you then move to a 20 megahertz bandwidth using 2x2 MIMO, HSPA Plus can achieve a maximum rate of 168 megabits per second and LTE 172. So these technologies are very comparable in terms of their performance within a given bandwidth. And that is another reason why both technologies will continue to exist for several years to come. But we do know that eventually some technology will become predominant. We all expect that to be LTE, but when will LTE become dominant? Well, this graph here of annual handset shipments by technology shows that it's going to be a while before LTE becomes dominant. So the biggest growth over the next several years is predicted to occur in HSPA. You can see this very strong growth rate here. LTE is this reddish line towards the bottom, and you can see it does have significant growth as well. So new technologies like LTE require significant changes to network infrastructure, and so they take time to become mainstream. Historically, about 7 to 10 years are required before multiple millions of handsets are shipped annually with a new technology. So LTE is just getting started on that historical curve, but so far it has actually been growing more aggressively than its historical predecessors like WCDMA. So from this graph, it's clear that for the near future, LTE and HSPA Plus will both be significant technologies in the wireless market. But what does coexistence of these technologies mean? Well, there's a balance that's going to be achieved, right? Operators, chipset, and devices are going to continue to support these multiple technologies. Subscribers won't really care which technology is used as long as their device continues to work as they expect and they can get their favorite applications to run. For multiple technologies to coexist like this, it becomes very important to make sure that handovers between them can occur seamlessly so that users don't see problems with their applications. And all of this means more challenges for device developers in terms of the complex designs and increasing time to market pressures. All right, that was a look at the market. Now let's spend some time talking about what the future for multi-format user equipment developers is like. So, today and for the next several years, wireless devices with multiple technologies are going to be developed and tested. All types of devices, data cards, modems, phones, smartphones, tablets, everything are going to use these multiple technologies. And these are the 5 most likely FDD technologies to be supported today and in the foreseeable future in a device. HSDPA Plus and WCDMA, GSM for voice especially, LTE. As we go further, this will expand more. And then Wi-Fi as well is a common technology to be included. So these devices with all these multiple technologies mean quite a big set of challenges for developers of devices. A balance has to be achieved between cost and flexibility. So on the cost side, some of the drivers there are time to market. Operators are expecting more devices and more quickly, and that drives time to market pressures. In addition, consumers want all of these brand new devices and the applications that go with them, but are not willing to pay a much larger price for them. And so price is being driven down as complexity is being driven up. On the flexibility side, usage time and battery life are always important and are increasingly important with more and more technologies that use more battery as well as more applications running at the same time on all of these devices. Inter-RAT, which stands for Inter-Radio Access Technology, this is the ability to test handovers as you go between different technologies. With devices that support these multiple technologies, this becomes more and more important to verify. Voice quality is not going away. People continue to expect the same quality they've seen from the very beginning, even as we move to an all-IP network. And, of course, faster data applications are always driving the complexity of the design as well. So it's important for a balance between cost and flexibility to be achieved for a wireless device to be successful in today's market. Development cycles continue to be compressed. Subscribers do not want to pay more for smartphones, even with all the additional applications. So UE developers have to continually balance the cost and the flexibility. But the verification of the design's performance is still essential. And consumers and operators with their high expectations are requiring these devices to perform well, as usual, even with these additional applications and higher data rates. So it's important to choose the correct tests and to perform them as efficiently as possible within the time-to-market constraints. So testing takes place at all parts of the development life cycle. And this chart shows just a very small portion of the life cycle towards the end, where validation and external to the lab testing is done. So testing takes place at all parts of the development life cycle, and there's all different kinds of tests. RF and Layer 1 tests are important early in the development life cycle for platform verification. They're also important at the end during manufacturing to verify that changes in lots in terms of hardware are not affecting the performance of the device before it's shipped. Some tests are used throughout the development cycle in all different stages. One example of that is a data throughput test. And some types of testing are more time-consuming than others and are typically done using automation. Today we're going to focus on 4 specific areas. We're going to focus on the functional performance testing of UEs. We're going to talk about what it means to do inter-rat testing, so testing between technologies. We're going to talk more about stress testing your device, how you can test with multiple applications and why that's important. And then we'll spend a little bit of time talking about lab IoT or interoperability testing, especially as it relates to doing testing for operators. So how can you balance the design validation and verification with time to market pressures? The most obvious way is to reduce the number of tests that you perform and the time it takes to develop them. That obviously has an immediate impact on your time to market goals. But just eliminating tests is not always the best answer because performance can be affected and field failures are even more expensive than failures in your lab. So streamlining the test processes and carefully choosing the appropriate tests to perform for your product are what is key. Okay, so let's talk a bit more about data throughput, which is one of the most important tests to be performed. So during validation and verification, UE functional and performance testing is one area that is very important, and data throughput is a big part of that. Here on the left, you can see a graph of data throughput over different conditions of the UE. This graph was made using an Agilent 8960 wireless communications test set, and the conditions can be varied in real time during a connection, which is what we're showing here. So what we did was we established an IP data connection using packet switch data. And we started to do a downlink FTP, so that means we're transmitting data from the network to the phone, from the 8960 to the device in this case. And then we varied the CQI value. So this is the channel quality indicator, and that value determines the level at which the phone can transmit data, so it determines the data throughput to some extent. You can see as we changed the value that the throughput stepped up to become a much higher throughput here than it started at. Then once we had changed the CQI values, we started here an uplink FTP. So in this case, we started transmitting data from the phone to the 8960. And you can see the throughput that was achieved there. At this point here, we stopped the downlink FTP, so now we are only transmitting data from the phone to the network. And you can see the increase in throughput that is achieved. And finally, at the end here, we changed the absolute grant values that the phone has. And these values are sent from the network down to the phone and determine how much uplink power is used. As the grants decrease, the throughput should decrease accordingly, and you can see that's what happened here. So graphs like this are essential to be able to look at your throughput performance under varying conditions like some of these here. But it's also important to look at statistical information, and that's what this graph on the right shows here. This was also made with Agilent's 8960. And we were testing here a dual carrier HSDPA device, so 2 RF carriers in the downlink, and achieving a maximum throughput rate of 42 megabits per second. So we're looking at the maximum throughput of this device and also testing the block error ratio and looking at the information the phone is sending up to the network, so the number of acknowledgments and non-acknowledgments that are received. You can also see here data for the serving cell and the secondary serving cell, so the two individual carriers here, and their data is displayed. So looking at the statistics is another way of determining, especially an easier way to troubleshoot problems if you see issues with throughput. Okay, continuing to look at data throughput, automation is another part of testing that can make things more efficient, especially for tests that are repeated frequently like data throughput, or for those tests that are performed over long periods of time. So here's an instance where it was really important to test across a wide range of environmental variations. So on the y-axis here is data throughput, and on the x-axis is variations in cell power, so from -100 to -40 dBm of cell power. And then each of these colored lines represents a different RF channel number, so a different URSIN that the phone is using. You can see that they are tracking themselves fairly closely, but that there are a number of different data dropouts depending on the cell power and the channels. And in particular, there is a pretty big failure here where for one channel, the data rate decreased sharply at high cell power and stayed that way. So you can see that it's important to test under these conditions and that an automated test can make this very quick. You can test all of these different channels and all of these different cell powers and find problems like this fairly quickly. All right, so another challenge for device developers is to look at voice and data continuity across technologies. So we talked about all the different technologies that can be supported today in different devices. There are many different types of handovers defined between all these technologies. And this chart here explains a few of those handovers with respect to LTE and 3G. So we're looking at long-term evolution and 3G or HSPA in this case. There are three main types of handovers described here. The first is not really a handover per se. It is a cell reselection. In this case, it's where the UE decides where to attach and become PDP active. So in this case, the phone is not in a live connection. Instead, it is just looking at the network and deciding whether to attach to LTE or to 3G. Once that's done and a connection is established with LTE, then there are two different main types of handovers that can be done. The first is a connection established and then released, commonly called a hard handover in the 3G side of the world. In this case, the connection is actually dropped and then reestablished on the 3G cell. And that allows the data to be maintained, but because there is a break in the data, it is actually called a hard handover or an RRC release handover. The third type of handover is the official EU-TRA handover, so this is another standard term for LTE. And in that handover, the data remains continuous during the handover between the technologies. So there is no connection, there is no disconnection and then reestablishment of the connection. It is just a continuous handover with the data operating. So those are the three types of handovers. Here on the bottom, you can see a picture of an Agilent E6621A PXT test set. And this is showing the setup for a handover between LTE and 3G. In this case, the PXT emulates the LTE cell, and an 8960 is used to emulate the 3G cell. And you can see here the different setups and the different statuses of the phone as the handover occurs. So it's likely that any device supporting LTE is going to support several other technologies. And testing the performance of the UE as it transitions across these technologies is really important. And best efficiency can be achieved with a reliable and repeatable test solution in your lab. Okay, we talked about stress testing a few slides back, and this is a slide which explains that in a bit more detail. So as more and more applications are used on devices, it becomes more and more important to look at your device's performance during those activities. That's sometimes called stress testing. So what this slide shows is an example of 3 different activities occurring at the same time. So first is an FTP, so a data transfer. Second is SMS, so text messages being sent and received. And the third is varying cell power. So this emulates the phone moving from one cell tower to another and the changes in power that are seen by the phone during that time. So all of these are done over a period of time. Of course, this is likely to be an automated test because of that. And different lengths of FTP were sent. So here there's a short one, here a longer period of time, and here a very short period of time. And then it also, at different times, several SMSs were sent and received. So you can see here there were a couple of failures that this test caught. First, when several SMSs were sent in succession, there was a failure caused by the SMS buffer overflowing in the UE. And this most likely occurred because there was an FTP going on at the same time and the cell power was dropping. Another failure was caught later on in the test cycle. Here we have an SMS being sent at the same time as a very strong FTP, so it was a very short cycle of FTP. And actually the device had a failure here and the FTP ended prematurely. So you can see that testing simultaneous activities can catch failures that you may not see if you were to test these activities independently. Another way of looking at the data and the common way of troubleshooting problems is to take a protocol log at the same time that this test is going on. This is an example of an Agilent Protocol Log using Wireless Protocol Advisor. You can then use the messages captured in this log and determine what was being done between the network and the phone when the failures occurred. As I said before, it's common to automate these types of tests and to then look at the results in a graphical form. So this is a picture of Agilent's interactive functional test software performing several different activities simultaneously and looking at data throughput while that is happening. So not only do you actually look for failures in the activities you're performing, but you might actually look at the performance of the device while these are going on. You might look at data throughput or battery drain, for example, while these activities are combined. And as I said, as more and more applications are rolled out onto phones and operating simultaneously, this type of testing becomes very important. You don't want your end users to find these failures. You want to try to find them in your lab first. So another challenge we talked about earlier is interoperability testing. And this is typically included with tests that you would perform on your device as you are trying to get the device accepted by operators for use on their networks. So these tests are commonly called operator acceptance tests or operator compliance testing. So the types of testing done here would be inter-rat again, so making sure that the device operates over the different technologies supported by that operator. Battery drain is also very important. Interoperability tests mean how does your device work on the network. This shows once again, an example of Agilent's Interactive Functional Test, or IFT software, that has been adapted to do operator acceptance testing for intra-rat. And so, once again, these tests are frequently automated and are done over the conditions specified by the operator. And they look at things like, does the device hand over properly between all of the different technologies? what happens to battery life as the devices do many things simultaneously and try to transfer data at the maximum data rates. And then do they meet expectations for usage and standby time under those conditions as well? And then finally, of course, the most important thing as always is, does the UE really deliver on its specified data throughput? So those are the kind of tests done in these operator acceptance areas. So this just gives you an example of some of the challenges that are faced by UE developers today and some of the tools that can help to make the testing process more efficient. So Agilent Technologies has a full portfolio that can be used for the wireless UE device lifecycle testing. We have fast, high-performance instruments with results that you can trust. So down here on the bottom, we have the EXT, which is our next-generation manufacturing platform. We've talked about the 8960 already in a couple of slides. It's the industry benchmark for 2G, 3G, and 3.5G. And there is a new 8960 that is out now with power to test 3.5G technologies like dual carrier HSDPA at 42 megabits per second. And future technologies as well. There's also a PXT product, as we discussed earlier, that supports the LTE R&D lifecycle. And finally, our GS8800 systems can be used for design verification test and RF conformance test of 2G, 3G, and LTE technologies. Okay, that's a brief look at some of the challenges for multi-format UE developers. So in conclusion, HSPA Plus and LTE are here to stay. Both technologies are going to coexist. As we move into the future, who knows what could happen? There might end up being more mobile than fixed data transmitted. There will be definitely more LTE devices available on the market, but HSPA will still continue to grow, as you saw, at least for the next several years. So with this strong industry support and the market drivers for both technologies, coexistence will definitely be the norm for several years. And the very large installed base of HSPA networks out there and subscribers makes it a very simple decision for operators to continue to enhance their HSPA networks, especially given the comparable data rates that they can get with LTE. But there is significant investment going on in LTE and in the advancements to LTE that are coming over the next several years, so that technology is definitely going to accelerate. So wireless device developers today are accustomed to designs that support all of these technologies and will continue to need to meet the challenges of all of the technologies over time. The balance between cost and flexibility is even more important with these new wireless devices, and choosing the right tests to achieve the optimal test efficiency will become even more important as time goes on and time to market pressures increase, as well as the complexity of devices increase. So choosing the right tests that validate a UE's performance efficiently within the time to market constraints, achieve your optimal test efficiency. So thank you for attending today. Are there questions that I can answer?
Thank you very much, Jody. Thank you. We are right in time, as I can see. We have the intention is to have 45 minutes for the lecture and your presentation. Thank you very much, Jody. It exactly fits it, and that leaves you also some time for questions and answers. So you can send the questions now in the chat in the Q&A window of the WebEx, and Jody is here to answer the questions for you in the remaining time. So Jody, here's the first question on the two technologies that you have presented. Can you compare latency as experienced by the user for HSPA Plus and LTE?
Well, sure. I think that latency actually applies very much to the transmission times, as we discussed earlier. So for HSPA, the transmission time, or the latency, is about 2 milliseconds. And so that period of time is, as I said, 5 times faster than for WCDMA. But for LTE, it's about 0.5 milliseconds, so about 4 times faster than HSPA again. And that's one of the big advantages of LTE, is the ability to transmit data in a smaller period of time.
Thank you. Another question. You mentioned several times that it was important to test under varying conditions. What types of conditions should be varied?
Yeah, that's a very good question. There's a lot of different things that can be varied, and you saw some of the things that we varied today, which were things like cell power to emulate a phone moving and looking at performance as that occurs. It's also important to vary the channels that you're operating on. You might see different performance at band edges than you would in the middle of the band, especially when you're testing things like MIMO, for example. You can vary the power that the phone is transmitting at to see how that affects things. You can vary the channel quality conditions, so you could add fading to the test to see how the channel quality impairments can affect your throughput or performance as well. So those are just a few things, and it's an almost unlimited list of things that you could vary.
Good. Thank you, Jody. The next question. I agree that data throughput testing is very important. However, it is often difficult to achieve the theoretical maximum rates. What do you recommend?
Yeah, it's very true. Everybody talks about the maximum data rates. It gets a lot of press, even in commercials on television nowadays. But it's very difficult to test that maximum throughput, as you probably won't achieve it on a live network unless you test directly under a cell site at 3 in the morning when there's no other traffic around. So the best way to test it, at least initially, is to do that in a lab under controlled conditions when you have control of all of the different variables that can attribute and affect your data throughput. So it's important to have a direct connection to the phone, initially at least, to make sure that over-the-air is not causing problems with your data throughput. It's important to make sure that your servers are under your control and that no other activity is going on the computers that the servers are working on. Any kind of other activity on the PCs or computers you're using with the servers can cause degradation in transmission time and therefore throughput. It's important to have control of the device and the tester or whatever you're using to emulate the network in the lab, because all of the different settings and parameters for those devices and networks can cause additional problems with throughput. There's usually an optimal set of parameters that can be used, and sometimes it takes experimentation to find those. But once you find them, it tends to be very repeatable, and then you can start to do different kinds of testing to continue to verify that your throughput works under mobile conditions or faded conditions, etc.
Thank you, Jody. There is a similar question related to lab testing. The question is, the idea of testing simultaneous UE activities in a lab is interesting. Can you give me some more examples of activities that can be tested?
Wow, yeah. So activities, there's a lot of activities. As we get to more and more data applications, the best way is actually to test the applications themselves. So you saw in the slides that we did SMS and we did FTPs. And FTPs simulate data transmission, but you could also test, for example, email and making sure that email messages being sent and received can be achieved while you're doing something else, while the phone is moving, while SMS is being sent, while you're downloading a page from the web. You could also test maybe MMS is another example. So this is when you can receive messages with pictures or video in them. You can test that you can do that at the same time as you're reading your email, for example. So yeah, there's a lot of different things, and what's best is to look at the applications that are most commonly used on the device that you're developing and to make sure that you test those operating simultaneously.
Thank you, Jody. I can see at the moment 2 more questions. Before going to the questions, I encourage everyone on the line, feel free and use the Q&A window to submit your ideas, thoughts, questions to Jody. We will also handle it during this session. So one more question, Jody. I can see Interat handover testing is useful. Knowing that the transitions between technologies are successful is necessary, but isn't the UE's performance during the handover important also?
Well, definitely. That's what you want to look at, not just at whether the handovers are successful, but also at whether you can keep your data throughput going, for example, while the handover happens. So it's very common to test data throughput and also to test battery life while you're handing over between the different technologies, especially, for example, if you're handing over between LTE and GSM. There's a significant difference in battery life there. You want to make sure that you're able to maintain the battery life you're expecting and the usage time you're expecting during these handovers. So yeah, you definitely need to look at your device's performance while these handovers are happening. RF testing is another way of looking at it. You might look at your device's EVM performance to make sure that it doesn't change as you're handing over.
Good. Thank you. Thank you, Jody. Questions are coming in. The next one, when will voice be introduced in LTE?
Well, I think voice is already being used in LTE to some extent, but there are so many different ways of using voice today that it's hard to answer the question, actually. So what's really being done today with LTE is that voice is not being supported in the network itself with LTE, but instead things like CS fallback, where a handover is done to an older technology to do voice is achieved. So that's typically done with C2K or with GSM today. Voice in LTE itself will be an IP, voice over IP implementation, and that is being discussed right now, but I'm not exactly certain when it will happen. I think it will start to be implemented in phones very soon, but when networks will roll out support for this is a pretty tough question to answer.
Good, thank you, Jody. So another question, this may not be directly relevant to this presentation, but is there a minimum data stream length stipulated to prevent breadth of spectral mask bounds? These 2 questions. Stipulated to prevent breach of spectral mask bounds.
Okay, so there are, when you're doing data throughput testing, the standards have a length of data that they require you to test. So basically you need to use a certain length of pseudo-random data in order to perform a complete test to look for things at things like block error ratio. So yeah, I think that there is a minimum data stream length that is recommended for test. I'm not certain about the breach of spectral mask bounds, but I think that there is a set of standards which will help you to determine what the minimum data stream length should be.
Good. Yes, for anyone on the line, so you can always send questions to Jody afterwards. We will send you also Jody's email address after this session, and feel free to contact her for any questions you have related to this session. Another question, Jody. Any thoughts on doing channel emulation and fading during Interat handover?
Yeah, it's really important to do fading during intra handovers, I believe, because once you verify that your intra handover is successful, you know, in a fixed environment, the most important thing to do next is to verify that you can do that handover in a mobile environment. And so you might start by doing that testing in the lab and varying your cell power to emulate that. But the other thing that's important is to look at fading, because as you move, of course, your reception is going to change based on the things around you, and fading is one way of emulating that in your lab. And I think it's pretty important to look at that while you're making sure your handovers happen and while you're making sure that your data throughput's not affected by the handovers in a faded environment.
Great, thank you, Jody. So if there are any questions, if you have questions also after the event or want to ask these offline, don't hesitate and feel free to contact Jody on the address you will be seen after this session. So as said before, this is a recorded session, and you will receive all information in an email where you can get access to the recordings and also see the email of Jody, and you can send additional questions to her. I think we are at the end of the event today. So we have passed through the presentations and questions. And thanks again, Jody, for your time and the very interesting topic you have presented today. Before closing, just to mention for the people on the line, after the session there will an evaluation form will pop up on your screen. And please fill out this form, and we appreciate your feedback on this seminar. So now we have reached the end. Thank you again for your attendance today. I wish you all a nice continuation of your day. Thank you, and bye-bye.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.